Chcel by som medzi nami privítať momentálne Milana Plžíka z Grafana Labs. Milan is a software engineer at Grafana Labs working on cloud platform team that provides international cloud platform services to the rest of the company, working mostly on low-level infrastructure, and his current focus is automating Kubernetes cluster upgrades. And also his topic of this presentation will be upgrading Kubernetes clusters the hard way. So, stage is yours.
Thanks a lot. So, hello everyone. My name is Milan, and as said before, I'm at Grafana's cloud platform team, which is basically the team that, well, platform team now, which is basically the kind of internal team that actually manages the internal infrastructure, ranging from low-level infrastructure provisioning up to the cost management, networking, or releases CI/CD, whatever. So we're the middleman between our product teams that are running their products in there, such as Member, Loki, hosted Grafana, and any outside cloud service providers that are providing services to us. So we're trying to basically balance between what our product teams need and what is necessary for to run correctly on the cloud service providers. Like, communication goes both sides. We basically escalate our internal issues to them. We communicate the stuff that's important that the cloud service providers are telling us to our internal customers and stuff like that. So I've been working mostly on Kubernetes upgrades for the past few quarters. And although it might seem to be quite a simple task to do, it turns out the reality might be much more complicated than that. Especially, well, ironically, in the cloud setting. So, if it's that difficult, why do the upgrades at all? So, firstly, because there's a lot of shiny new features coming up with every minor Kubernetes release, and who wouldn't want those? Well, that's true, partially. The truth is also that because the cloud service providers only support recent versions of Kubernetes, and as we all know, no support means no SLA for the clusters, meaning that we're mostly on our own. And cloud service providers often align their Kubernetes offering support with the upstream Kubernetes support, meaning that the support goes usually like a few months past the upstream Kubernetes support. So it's actually, in average, like 3 upgrades a year, because that's how frequently currently their Kubernetes team does releases. And also, clusters that get too far behind with their version get auto-upgraded, meaning that, well, even if disabled, meaning that the cloud service providers are usually pretty gentle and start only upgrading the control plane of the cluster. But if the versions in the cluster starts to slip through the Kubernetes version SKU policy, they might eventually start upgrading also the node pools, which might be problematic if your workloads aren't exactly aligned with how a Kubernetes workload should work. So let's have a look at a little bit more details about the actual what we want to achieve here. So for our purposes, the upgrade goals are to keep up with the supported Kubernetes versions, just to make sure that we're actually within the supported SLA window, minimize disruption for the cluster users, be it our product teams, which are actually running their workloads, or even the user, like the external customers of ours, which probably wouldn't want to see too much of downtime on our service. And also to provide new bug fixes, features, whatever. The bottom line there is that these are not exactly ordered priorities, and they often shuffle around. For instance, a few weeks ago, there was an issue where EKS rolled out AMI image that had a fairly nasty eBPF GIT member leak issue. And if you happen to pick that up, it was quite inconvenient and had to be upgraded pretty quickly. So at that point, the risk calculations change a little bit, and you'd rather do a little bit more disruption and risk than having a buggy image run and eventually stop being able to launch your containers. So, and speaking of disruption, so this is the important thing here as well. Disruption is a state where there are no pods available to serve user requests. Simplistic definition just for the purposes of this presentation. But the bottom line is that there are two kinds of disruption. First is a voluntary disruption. This is a disruption that's triggered using the Kubernetes API or Kubernetes internal automation, whatever. And it's the kind of disruption that we're actually pretty much in control in. So we can affect this disruption multiple ways by doing kubectl delete if we want to enforce something, or actually configuring our workloads to not do any kind of disruption if there's a risk of problems. Then there's also involuntary disruption. That's usually the disruption caused by external forces such as machine failure, so on and so forth. So this presentation will focus mostly on the voluntary disruption, but as for the involuntary one, that's a topic on its own, because although it might not seem like that, this is happening all the time. So even if we not see that, at the scale of cloud service providers, there's a lot of stuff happening on the VMs. Like there's always some kind of memory issues, hardware failure, upgrades, or the servers get hit by neutrinos, you name it. And some of these issues can be quite successfully masked by, for instance, live VM migration, whereas some others, such as memory corruption or anything like that, can't be masked at all, and they just result in the VM going down, whether we like it or not. And this is basically an end scenario for us, because at this point we can't predict whether a neutrino hits a particular bit in memory. And the only thing we can do to avoid external facing issues to be really prepared for the worst and hope it won't happen. So this presentation will focus on the voluntary disruption mostly. So the way of Kubernetes upgrades. Kubernetes works best with the workloads that can handle involuntary disruption of a pod or two in a workload. That makes complete sense. Like ideally stateless microservices, if you just shovel one away, the others can step in and replace it with no issues. Note that any single pod, if deleted, if removed, causes an outage. There's no easy way to work around that. And at that point, we're basically just calculating the risks and trying to see how much of downtime we can afford. The automation for the Kubernetes upgrades, the automation usually drains each node and replaces it with an upgraded one. And along the process, it drains all the pods that are running on that node and hopes that they will schedule successfully on the new node. There are several mechanisms built into Kubernetes to make this as seamless as possible. Well, and then there's the reality of Kubernetes upgrades. Not all software is made equal, and that's especially valid for stuff that was designed before we were actually running stuff mostly in the Kubernetes clusters. So pre-Kubernetes software uses its own means of handling multi-node deployments. So there's a lot of software stacks that has its own draining and multi-replica master election algorithms implemented. And these are sometimes not exactly easily mappable into Kubernetes. For instance, we have a lot of SQL servers that do have some master-slave replication. Well, master replica replication, sorry. The problem there is that this doesn't map correctly into what Kubernetes expects. Like Kubernetes is quite egalitarian. So take any single pod, shoot it down, and the other pods should step in. This doesn't hold for the traditional SQL server layout, where if you kill off the master, the cluster of the SQL servers is for a moment unable to do writes because you only have the replicas that might be serving your database. So there's a new round of master election reconciliation needs to be done in order to make stuff running up again. So it's not as easy. For a SQL replica, that would be much, much easier because you usually only have to spin up new pod and either replicate the state, and while you're replicating, the other replicas can easily step in and serve the content. Some software supports running only as a single replica. So some software was written without any kind of multi-tenancy, multi-replica running setting in mind. So that's running that in multiple replicas in parallel can easily result in having lots of race conditions, stuff like that. And usually we don't want to happen. And also, even for stuff that's fairly okay-ish running in a cluster, there are a lot of edge cases that we can inadvertently trigger, such as having one big Kafka cluster that's serving a lot of small product clusters. And if we do too much or too quick rolling restarts in those product clusters, suddenly the Kafka gets overwhelmed just by pulling all the data in, because a lot of paths has restarted almost simultaneously, and triggers cascading failure, which is not something we would like to do. So TLDR, there is some software is fairly sensitive to disruption and needs special handling, whether we like it or not. So with that in mind, how to minimize disruption for sensitive workloads, as we talked before in the previous slide. So firstly, and maybe a little bit, ironically, don't run it at Kubernetes. There's some software that doesn't fit the Kubernetes concept that well. And consider either using the CSP's offerings. We're upgrading Cloud Kubernetes, so chances are you do have some offerings that you can use in place of on-prem SQL servers or object storage or whatever. And the CSPs have actually invested quite a lot in developing the automation for this and trying to make it as seamless as possible to use. It might not be, it's not a one-size-fits-all solution, but it might be good enough for you. At least it might be able to prevent you from hiring a separate databases and storage team just to get your SQL server, MySQL clusters handled correctly. So this is something that should be definitely considered. The other thing is running the workloads on VMs instead. So if Kubernetes is too disruptive, VMs are much more stable and they can still go down, but there's an SLA provided by the cloud service providers, and they go only down if there's something really bad happening. So not from the reasons that the control plane decided that we're spending too much because these VMs are underutilized, let's just shoot up this VM. So the other thing is run it on Kubernetes, but carefully. So there's always a way to be a little bit more gentle to workloads, meaning we can use a dedicated node pool or node group to run the workloads and retain some lifecycle control, meaning we won't be that much susceptible to disruption that's caused by a generic full-packed Kubernetes node. And also we can trigger the node pool upgrades for separate node pools. So there's at least this knob for fine-grained control. And we can, for instance, create separate node pools for each database we use, or alternatively for each workload that we use that we know that uses the common database backend, and slightly throttle any kind of rollout restarts that might happen over the course. And the other thing is we can use existing Kubernetes operators. So the operators are basically software that tries to bridge the Kubernetes API and whatever is happening inside the distributed software that might not be fully Kubernetes native, meaning translating all the magic state, what's the current state of replication for this node? Is this node fully populated or not yet whatsoever? And once Kubernetes knows about these details, where in Kubernetes terms, it might be a little bit easier for it to handle some disruption. And it also helps with recovery. So if an Elasticsearch node goes down, the operator can easily notify the Kubernetes cluster that maybe there's a new node spinning up, there's a replication happening, please don't do any kind of disruption right now, and similar things. So it might be able to do some things. It's not like a silver bullet, but it definitely helps when running some software that's not designed to be totally Kubernetes native. And the last thing is embrace Kubernetes. Well, that's probably easier said than done, because it's fix the code to be Kubernetes native or implement it in operator yourself, single sentence, even with exclamation mark at the end. The truth is that if there's no existing operator and the built-in Kubernetes controllers such as deployment or stateful set or daemon set don't fit the bill, well, it's probably the way to go, but involves a lot of coding and debugging, which usually needs to have its price justified because it's a software development issue. It's not a DevOps issue anymore. And with that, now we have our Kubernetes cluster with a lot of workloads in there running. Let's have a look at how to manage the upgrade. So firstly, there's the CSP Way. That's probably the most easy in the terms of maintenance or whatsoever. It works as simple as it sounds. So it deletes the old nodes and the pods on it, spins up new nodes, running new version of Kubernetes, and respins the new pods there, the deleted pods there. And the trouble, as usual, is that deleting a single replica workload pod causes an outage. Well, obvious one. The bigger workloads still need to correctly communicate their health to avoid outages. Usually, this should be okay. Sometimes there might be corner cases. And the problem is that there's little control over the process, meaning that once we start the upgrade, the CSPs usually, well, either run the process until it fails, or like there might be a knob that actually allows to stop or cancel a node pool upgrade, but it ends up in an intermediary state where you actually have half of the nodes upgraded to one version, the other half to the other version, and it's not a totally good idea. So the meta algorithm is basically upgrade control plane for each node pool, and each old node in the node pool pre-spin up a new node that's already running in the new Kubernetes version, and for all the pods on that node, delete the pod and hope for the best. Well, delete the pod is a little bit more intricate than that, because there are Kubernetes-native control mechanisms for this. So there's the pod readiness health probes that actually allow Kubernetes to see whether the pod feels healthy, as in the pod is okay-ish and doesn't need to be killed. If a pod gets unhealthy for a too long period, Kubernetes just kills it off. Or ready, unready, which might be as well used for indicating where there is the pod has pulled all in the data that it needs and can be included in load balancing or not. So then there's controller rollout strategy. So actually, Kubernetes controllers are able to provide you with, for instance, extra pod if you're doing Kubernetes rolling restart. So the magic there is that this is not a regular disruption, as in deleting pod, but instead there's a mechanism to do kubectl rollout restart. Tells the controller that it might tell the controller that there's also a need to spin up new search pod. Then we have pod disruption budgets, which attempt to control how many of the pods can go down. And if there's a request to delete more pods, it will get blocked. This is an important bit because it also, so there's a difference between pod deletion and pod eviction. We'll come to that a little bit later. We have priest-up hook that basically tries to execute some code before the actual pod gets deleted, and then we have Kubernetes object finalizers, which is a sort of magic metadata for Kubernetes objects that gets added by finalizers. And if a Kubernetes object ever gets deleted, it doesn't get deleted instantly, but instead its deletion time is configured to be some current timestamp. And then the Kubernetes waits until the finalizers all go through the object, which they should. They should watch all the objects for which they do have the finalizer metadata configured. And once they remove all the finalizers from the Kubernetes object's description, it gets deleted. So it's basically a helper to make sure that some actions are run before the object gets totally deleted and forgotten from Kubernetes. So then there's the manual way of upgrading, which is much, much more tedious, but also much more safe. So this means basically a node pool migration. So instead of using CSP's button to just do the node pool upgrade, we can upgrade the control plane of the Kubernetes cluster and then start spinning up new node pools. Those new node pools will be running new Kubernetes version, which is totally fine for us. And then comes the hard part, which is migrating the content of the old node pool to the new node pool, and also ensuring that stuff really works out correctly. This usually means that we need to taint the old node pool with some taint that prevents any new workload spinning there. That usually means the no schedule taint. And then proceed with careful pod deletion. The important bit is that now we're in the control of deleting the pods, and we can implement a lot of our own safety checks and any kind of magic that we need to ensure that we don't break our production totally. The drawback there is that this gives a lot of fine-grained control to the human operator, and thus is also quite tedious. Like, this works for a few tens of pods, but if you have like hundreds or thousands of pods running in your cluster, you probably don't want to drain all the pods with a single command, because you, for one, risk that you usually forget that sleep 30 in your for loop that's supposed to throttle the pod deletions. And the other thing is that one is easily able to miss out something, like there's plenty of space for human error, which we should probably avoid. So then there's this approach of controlling the upgrade using the code, meaning that instead of writing a normal operator, we would be writing a sort of kind of upgrade operator that carefully tries to do the manual thing. For each node in the old cluster, it basically tries to use eviction API to mark a pod for deletion. The difference between deletion and eviction is that the eviction API tells Kubernetes API that this pod should get deleted. We'd like to have it deleted, but let's respect all the rules that are set in the cluster. So PDB gets respected. Any other things are totally getting respected. If there are conditions that would be broken, like PDB, the pod's deletion would just stall and not get deleted until the conditions are met again. So this is a fairly safe thing. And also a few hundreds of lines of code from our operatorless, because we don't need to care about PDBs explicitly. In this code, we can easily special case our own workloads that are problematic and implement any kind of waste of timeouts necessary. So this is a operator, but it only works for upgrades. That's the important thing, and it still doesn't prevent any disruption that's not related to upgrades. But for purposes of this presentation, well, it fits the bill. For any kind of more intricate things, you probably still want to use a normal operator. Oh, and the bonus: avoiding single pod outages. So what I repeat a few times across the presentation is that single pod outages are problematic because, like, if you have single replica workload, like killing the pod, well, it kills the pod and the whole service with it. So the bottom line is that there's really no way to really avoid that, but there might be some compromises if you are able to run the two pods of the replica of the workload for at least short period of time. In that case, you can use that property of deployment controller, deployment manifest that actually allows you to configure a search pod. So with that manual process for upgrading, instead of doing a kubectl delete pod or evict or whatever, there's a way to trigger kubectl rollout restart, which is able to spin up a search pod before the old pod actually gets deleted, and this does precisely the thing we want. It spins up a new pod, waits until it's healthy, and then tries to spin down the old pod. So ideally, this shouldn't be too problematic and should work. The only problem is that it only works with that special kubectl rolled restart command. If you do any kind of kubectl pod delete pod, the stuff goes directly to the pod, and the pod gets terminated before the controller actually realizes that it should start spinning up new pod. So there is this gap where you don't have anything serving. And the experience at Grafana Labs. So how do we run our infra is that we have a lot of services that are already Kubernetes native, meaning that we don't need to care too much about actually running about how to train them properly. It mostly works, and it works correctly. There are some special cases, though, special snowflakes even. So hosted Grafana. So if you try to run Grafana in a multi-tenant setting, it's not that easy. There are some bits that are not designed to be ran in a multi-tenant setting. Well, sorry, multi-replica setting. And if ran for a long time, for instance, there would be extra alerting rule evaluations, all stuff like that, which is not something that we want. But this is exactly the setting I talked about previously. So for a short period of time, it's actually okay to run two Grafana pods at once. So when we are doing Kubernetes upgrades, except for running upgrading the other things, for hosted Grafana, we do the special node pool migration when we spin up a new node pool, which is a separate node pool just for hosted Grafana, and then carefully do kubectl rollout restart on the service so that it actually spins up the search pods and the search pods land on the new node pool, which is careful and mostly okay-ish. It doesn't break too much. And also, for more sensitive services, we throttle their upgrades. So we do have a manual sort of upgrader that goes through our sensitive workloads and tries to carefully restart them and wait until they become fully healthy. It does even a single node throttling, meaning that it doesn't try to drain the whole node at once. Instead, it really takes care to only drain few pods at the node at the same time, wait until the controllers indicate that everything is healthy again, then proceed further. And with that, we're able to do stuff fairly okay-ish. Meaning there's always some fun associated with upgrades, because it's still mass restart, but it's fairly under control, and we're quite careful and adjusting the process as it goes. So, and what about the future? So, our heading right now is to converge on the CSP upgrade process, which is probably the cheapest way and also the way that it probably should work. But chances are with that this won't ever happen. Like, the world isn't ideal. We have some ideal things in physics and stuff like that, ideal gas, mass point, and so on and so forth, but this is not the case. We're in the real world, and there's always going to be workloads that might need special casing. So for hosted Grafana, there are some efforts to make that a little bit more streamlined. But as we are trying to do that, there are some new workloads popping up that might need special casing as well. And we're looking into Carpenter, which is a different take on node group scaling, so for now on EKS. And that's actually a little bit of opposite to what we're doing, because upgraders, in the sense of Carpenter, are not something that we would need to just start, device a week or two for, and then finish. But instead, Carpenter allows to configure a TTL for each node in the node group that it manages. So instead of like really start-stop kind of upgrades, we would have continuous upgrades. Carpenter would just pick the most recent version that's running on the Kubernetes master nodes, and once a node's TTL gets reached, the node will get deleted, and instead of it, a new node with the current version would be spun up. So we'll see how stuff goes from there, but it's really fun to upgrade Kubernetes clusters that are running a lot of production workloads and see the differences between what's Kubernetes native and what is not exactly. So with that, this is my last slide. So I'm open to any questions you might have. On Slido or in person?
Can you read it? Because I don't have
Oh, yep. I think I'll do my best. Okay, So what was your worst experience with an upgrade? The worst issue? What was your best experience with an upgrade? Everything was working well. Okay. The worst experience actually happens quite often before the actual upgrade. Okay. The worst experience ever, but that's not going to happen anymore, is, I think, 1.19 to 1.20 or something like that. Back in times when Grafana clusters had a little bit of more like custom tweaking to it. So we were running on GKE, but we're using the GCLB directly to address. Basically, we were using GCLB pointed to a instance group that was created by Kubernetes clusters, meaning that so our upgrade process inadvertently changes instance groups that are backing any kind of node pools that we have. And if we were really pointing manually a GC load balancer to a specific instance group, chances are that you at some point forget to add the new instance group to the actual backend, and well, stuff can get really broken in funny ways then. You basically, everything works until you have at least one. So our system was designed that if there was at least one node in the old node group that was supposed to be deleted, everything was just working fine and routed correctly. Once the last node from the old node group got deleted, everything just went blank. And I think there was an outage about this as well, but I don't remember exactly. Right now, we moved to a more streamlined solution that actually is in line with what the GKE is trying to design. So that works much well. And, well, other than that, just TLDR, any kind of breaking API changes are always a challenge, and trying to be sure that all the Kubernetes objects you are using the correct API version and that nothing breaks. That's the usual chore we need to do before each upgrade if there's any breaking change. And it's a lot of fun. The best experience usually, so that's actually a continuous process. We started to automate our upgrades quite a lot because we're running now a fair amount of clusters which are fairly big. So we wrote a tool that basically worked with our internal GitOps repo and tries to submit PRs for each change. So we actually started doing a little bit no-ops automation, if you know the term. It's basically writing a code that only tells you what to do. So you'll write a program that basically shows you the steps that you need to do and maybe checks whether the steps were actually done. And then you can slowly automate the steps and try and make it more and more hands-off. So we did that, and that slowly allowed us to basically automate ourselves out of the low-level per node pool upgrades. So right now we have per cluster upgrades with us only approving the PRs that the tool generates, and it's much less brittle than it was before. And we're still moving toward eventually having maybe at some point single-click cluster fleet upgrade, if such a thing ever exists. But we'll see. So how do you perform controlled node drain? Great question. So firstly, I'm not sure if that question was in a setting of automated or manual node upgrades, because for manual node upgrades, it's quite easy. So tainting the node so that it actually so that the Kubernetes scheduler will avoid that node ever, and not schedule anything there. And then basically our tooling just fetches the list of the pods that are running there, which is fairly easy using Kubernetes API, and tries to figure out firstly, for the sensitive workloads, the owner of each pod and generate kubectl rollout restart on those controllers so that those pods get moved to other nodes. Well, and for the remaining pods, it just uses the eviction API. And the last question, what is your time estimation upgrading Kubernetes from 1.20 to 1.25? Oh, that's like 5 versions. To be honest, I'm not totally sure. Currently, a upgrade between minor versions takes us around week, more like week or two of time. So multiply that by 5, and you'll end up with a quarter or so. If we went from really 0.20 to 0.25, we could probably take some shortcuts there, and stuff would go easier. But still, the manual process, like we have big clusters that take days to completely upgrade. So I wouldn't probably go lower than a week per total upgrade. If we are completely sure, we would be re-rolling all clusters at once without any canarying and stuff like that. But we are not in a race to upgrade the fleet in the shortest time, but to upgrade it the safest way we can. Okay. Oh, last question. Do we still have a few seconds of time? Okay. It's not a matter of time upgrading from 1.25 to 25, rather the amount of pain to manage. So from that point of view, it really depends on the tooling at hand. If we had to do that in the way that you are doing 1.17 or 1.18 upgrades, that would be really painful, because that actually involved manually doing a lot of stuff on per node pool basis, and then running our tooling to drain the node pools, stuff like that, even manually adjusting the instance groups. That was really painful, and I wouldn't want to do that anymore, because it's a recipe for disaster. With our current tooling, it's much easier. It's more about tracking which clusters did get upgraded, which not, where something did break, because some things do break, especially on dev clusters where people are not as diligent with keeping up with not crash looping stuff. But depends. That's it.